So let's go into the last topic, and we're going to talk about what are called colligative properties. Now, I know it's a tough word to say, colligative properties. A colligative property is a property of the solvent that changes when you add solute. Okay, so now, up until this point, whenever we've talked about molarity, molality, mole fraction, etc., we've basically always been talking about the solute. But now, for colligative properties, for the next three factors, we're going to talk about solvent specifically. This is an important change. The first one we're going to talk about is vapor pressure. Vapor pressure is abbreviated with VP, and vapor pressure, by definition, is the pressure exerted by a vapor on a liquid. Now, what's a vapor? Remember that a vapor, the key to being a vapor is it's a liquid that has changed, that has evaporated into a gas. Okay? So it's in the gas form, but it was a liquid previously. What's the difference between a gas and a vapor? Simple. O2 is a gas because oxygen is always a gas. But H2O can be a vapor. Okay? Is it possible for H2O to be a gas? Absolutely. If I have a chemical reaction that produces a lot of heat, then yes, I can produce water as a gas. But if the water is a liquid and it evaporates, then it's going to be a vapor. So vapor pressure will drop when solute is added. Now, let me show you a little visual so you can understand the vapor pressure a little bit better. Let me erase that. Okay, so this is a visual representation of vapor pressure. What has happened is the water molecules have escaped from the liquid phase and are now floating around all over the place up above the liquid. Some of them are going to bump back into the liquid. Okay? When they do, that's your vapor pressure. Okay? So when those gas molecules bump into my liquid phase, they exert a pressure back on the liquid. When that pressure, when they do, that's the vapor pressure. Okay? So now, let's talk about what happens when we add a solute. Okay, now, remember, think about this. The only molecules that could possibly evaporate are the ones that are along the surface. Okay? You can't evaporate if you're down here somewhere. It's not possible because you're going to bump into other stuff as you're trying to get up. So the only molecules that can escape into the vapor phase are these molecules along the top. Well, let's say I throw a solute in there. Well, some of the space that was the surface and now was liquid, was the water, is now solid. Now solute. Okay? So now, what's happened? Well, look, the number of water molecules that have the ability to escape into the gas phase has drastically decreased because these solute molecules are blocking the surface. Okay? So they physically are blocking the water molecules from getting out of the liquid phase and they keep them in. Well, if you're blocking the liquid phase from getting into the vapor, it means that there's going to be less molecules up here putting pressure back down. And that is why vapor pressure will decrease when you add a solute. Now, I can calculate this. And I'm not going to actually, I won't test you on this next piece, but you really need to know it because it is important. It does connect back to gas laws. So, this is what is called Raoult's law. O-U-L-T'-S law. It looks a lot like Dalton's law, but it's not. Okay, it's called Raoult's law. What it means is the vapor pressure of a sample is equal to the mole fraction of the solvent in the solution times the vapor pressure of the pure substance. So, for example, if I have pure water in a jar, okay, it will have a vapor pressure of exactly 1 atmosphere because water can evaporate at regular atmospheric pressure. Once I start adding solute, this mole fraction will start to become a number less than 1. Okay? So as the mole fraction becomes a number less than 1, and I multiply it by the standard vapor pressure, you'll see immediately that the vapor pressure begins to drop. So that's how I can calculate the vapor pressure of a solution from the standard pressure and the mole fraction of my solvent. Okay, so that's vapor pressure. Now let's talk about boiling point. Boiling point is connected to vapor pressure because here's the key. This is the most important statement right there. Boiling occurs when the vapor pressure equals the atmospheric pressure. So in other words, when the amount of vapor coming out is exerting the same amount of pressure on the liquid as the atmosphere did, that's when boiling will occur. So think about to your house. You make pasta on the stove. You're heating the pasta. You ever see steam coming out of the pot before the water actually boils? Well, that means those molecules have gained enough energy to escape from the liquid phase into the gas phase. But because there's not enough vapor pressure built up of the water molecules, that means the substance will never boil. So a couple things that people love to do is, if you're like me, you have a vent, the hood above your stove. And I like to turn on the vent so that it blows the steam all over the place. Well, think about it. If I'm blowing the steam away, I'm reducing down the amount of vapor that can exert pressure back onto the liquid. And so it actually takes longer for my water to boil if I turn on that hood. The best thing you could do, obviously, is put a lid on it. If you put a lid on a pot, if you think about your pot and your water, well, if you put a lid on it, when those molecules come out, they have to immediately bump back down. There's nowhere for them to go with that lid on the pot. Of course, you got your little handle. Don't forget about the handle on the pot. So the molecules get trapped, and you allow the vapor pressure to build up even faster. You may have even noticed that sometimes when you can kind of hear the water boil, and you open up the lid, and it stops boiling as soon as you open the lid. It's because you released the vapor pressure, and now it's going to take it a time for it to build back up. So when I add solute, it's going to increase my boiling point because it's going to take longer for me to get to that get to the vapor pressure to be equal to the atmospheric pressure because I've lowered the vapor pressure. So if I want to calculate how much the temperature has changed, I'm going to use this formula. Delta T, this is delta. Delta is a Greek letter, which means change. So this is the change in the boiling point is equal to the boiling point constant times the molality of the solution. Okay? So, now, what's this number here? This 0.52 is the boiling point constant for water. Since I'm always going to give you water as your solvent, remember this is in terms of the solvent, so I'm always going to give you water as your solvent, I'm going to give you this KB. You do not need to memorize this. It will appear on the equation sheet, and you just plug in your numbers. Now, this, remember, is the change in the boiling point. Water normally boils, the boiling point for water is 100 degrees Celsius. So that means you're going to add temperature to this, add a number to this. So as the boiling point goes up, this temperature will rise. Will it rise a lot? No. 0.52 is not that big of a number. Okay, so it's going to require a lot of solute in order to raise the temperature just a whole degree. Okay. Here's a little manipulation of that vapor pressure situation.
I know we normally think of boiling water.
So I'm going to commentate over the top, and I'm going to actually jump ahead a little bit. So what this guy did was he took a container of water, okay, and he hooked it up to a pump, and the pressure gauge for it is here. And you can see what he's doing is he's actually vacuuming out the pressure. So he's vacuuming out the air that's at the very top. You could see this is the air pressure coming out. So it's creating a vacuum situation. So all the air on the top of this jar is actually being sucked out of the jar at this moment. And what he's doing is he's lowering the atmospheric pressure. So remember that water molecules will naturally evaporate. If you've ever left a glass of water out overnight, you'll notice that the glass of water is just a little bit lower than it was the night before because the water molecules are going to evaporate on their own, just using regular old air temperature. So some molecules are evaporating out. Oh, look at that. And notice what happened immediately. All of a sudden, boiling occurs. Okay, so what has happened here is the atmospheric pressure inside has decreased so much that the vapor pressure equals the atmospheric pressure, and he's actually boiling the liquid. Now, what's kind of freaky about this is notice where the boiling is occurring. Is the boiling occurring where it normally does? No. At home, you have a pot of water, the boiling occurs down here at the bottom. But in this situation, the boiling occurs at the top, even though I moved it. Boiling occurs at the top because that's where the molecules are escaping the fastest. No energy is being transferred here. The temperature of this is still whatever the temperature it was before, so it's at room temperature. So you can see that you can actually boil water using a vacuum pump and never actually heating up the liquid. And when he's done, the liquid is still room temperature. So now let's talk about the last colligative property. The last one is one that we are very familiar with as we just got out of the winter, as we're just getting out of the heavy snows, and that's freezing point. When you add solute to a container, you are going to decrease the freezing point. Okay, so freezing point goes down when you add solute. This is the formula you're going to use. So it looks just like the boiling point formula, except it's for freezing. Delta T will be your change in the freezing point. Kf is your freezing point constant. This is again for water. And M, once again, is your molality. Now your freezing point for water, because again, water is going to be your main solvent, is going to be 0 degrees Celsius. So in order to get water to freeze at a lower than 0 degrees Celsius temperature, you're going to add solute. And this is why we put salt on the roads in the wintertime, because by adding salt, you are preventing the water molecules from freezing at regular freezing temperatures. Now let me give you a semi-visual. My drawings are not quite up to par sometimes. So let's imagine that we have pure water and we have a solution. In order for something to freeze, remember back to the intermolecular forces and heating and cooling curve PowerPoint, in order for something to freeze, it has to create intermolecular forces with the stuff around it. Okay? So these molecules are forming intermolecular forces with everything around it. Well, what if, instead of it being a pure substance, there was something else mixed in? And it doesn't require a lot. Let's add that solute again. Okay? Now, in order to form those intermolecular forces, it's going to diminish how many and the strength of those intermolecular forces. Notice the number of connections that each molecule can make has drastically decreased. And also, in order to form some of the ones that are on opposite sides of the solutes, those molecules have to get a lot closer together. Remember, molecules don't like to be closer together. So in order to get them closer together, we have to drop the temperature. Okay, and as we remove energy from those molecules, they will eventually form those intermolecular forces and freeze. So that's freezing point depression.